Hello and welcome to our online lesson. I am your teacher, Mr. Steve Getau, and I do welcome you to our channel at Steve Getau 660. Allow me to take you through the organization of our channel. We have put all the videos in mathematics and chemistry in form of the playlist. So viewers, once you get to the YouTube channel, search at Steve Getau 660, click on the playlist and you'll find playlist for Form 1 up Form 4. In this lesson, we've placed it under Form 3. In that folder, you'll find Form 3 Chemistry and also Form 3 Mathematics. Once more, thank you for joining us. Kindly do subscribe, share, comment, and like so that any moment we upload a new video, you'll be one of the first people to be notified. Straight away, let's get to the lesson. In the Form 3 topics and chemistry, the first topic is the gas laws. In this, we study properties of gases in terms of how they relate to pressure, volume, and temperature. At the gas laws, we shall basically examine four main the gas laws, although we have sub-laws in that. The four main gas laws will include, one, we have Boyle's law. Number two, we have Charles' law. Number three, we shall talk about the combined gas equation. The combined gas equation law, which is a combination of the principles of Charles and Boyle's. And number four, we shall talk about Graham's law of diffusion. Graham's law of diffusion. So, viewers, as we take off in this lesson, I would like you to know that we shall examine each of these laws. We shall have some examples in each case, and then in part 2, we shall have calculations, especially so in Graham's law of diffusion. This is the most commonly tested area on the gas laws. That is the Graham's law of diffusion and the calculations that are there. Do watch up to the end, because at that point we shall be able to see the common testing areas whereby we have the comparison of how gases diffuse when they are same volumes, and how we go about it when we are talking about different volumes. Join me up to the end. Number one, what is Boyle's law? Boyle's law states that for a given mass of a gas, the volume of that gas, the volume of the gas is inversely proportional to the pressure, is inversely proportional to the pressure at constant temperature. So this is something that is very, very important, in the sense that we are able to meet the particulars that are very important. That for a given mass, or rather sometimes you say for a fixed mass of a gas, the volume is inversely proportional to the pressure. Inversely proportional to the pressure, provided the temperature is kept constant. This is best illustrated by the bicycle pump. As you decrease the volume, the pressure inside the pump is increasing. That is a case of inverse proportion. That is, the volume is inversely proportional to pressure. As volume is increasing, pressure decreases. As pressure is increasing, volume decreases. And this can be shown when we remove the proportionality sign, we get V is equal to a certain constant K all over P. And that one can further on be shown if we multiply both sides by P, we get pressure times volume is equal to a given constant. Now, since we can change conditions of pressure and volume, it takes us to a situation whereby we can illustrate this one as when the pressure 1 multiplied by volume 1, we shall always get that being equal to pressure 2 times volume 2, and that is always a given constant. And that way, we are able to generalize and summarize the law of Boyle's. So maybe to make sure that this is quite visible, allow me to write in black. And we are saying P1 V1 is equal to P2 V2, and that is equal to a constant. So we are saying this is the summary of Boyle's law. Now let's look at number 3, the law of Charles, or what we call Charles' law. Charles' law. Charles' law states that when we have a fixed mass of a gas for a given fixed mass of a gas, we look at two conditions. We look at the relationship between volume and temperature, keeping the pressure constant. So we find that for a given mass of a gas, the volume of the gas is directly proportional to the temperature, at constant pressure. So this can best be illustrated by the use of a balloon. In a balloon, we have air enclosed, such that when we raise the temperature of the air inside, the volume occupied by the air will increase. That shows increase in temperature leads to an increase in volume. The pressure inside the balloon will at first increase, but later on stabilize, creating a constant pressure. However, the two items that will change are volume. Can you illustrate that here? We have changed on the volume, and we shall have a direct proportion to the temperature at constant pressure. So how is that one illustrated? We can illustrate that and say volume is directly proportional to temperature. Or what does that mean? If we remove the proportionality sign, we shall get that volume is equal to a given constant of proportionality multiplied by the temperature. And that means what? That means if we divide by temperature on both sides, we shall have volume divided by temperature is equal to the constant of proportionality. And now, since the conditions of volume and temperature can change from condition 1 to 2, then we shall have the rho being put at V1, first condition of volume, first condition of temperature being equal to the second condition of volume and over the second condition of temperature, and that one is all constant. And that summarizes for us the Charles rho of gases. So, in short, we are able to see how the two laws are relating. At this point, I would like us to look at the combined gas equation. Combined gas equation. What happens when we are able now to combine the two? That is the first row, equation number 1, and equation number 2. And that leads us to number 4 in our serialization, combined gas equation. Combined gas equation, which is basically a law on its own. Here we shall have that P1 V1 is equal to P2 V2 and V1 over T1 is equal to V2 over T2, which when combined, it gives us the relationship. We are able to see V1 relating to T1 in an inverse relationship here. V1 relates directly to P1 and V2 relates directly to P2. So maintaining that relationship, we shall be able to get P1 relating to V1 as here, and V1 relating to T1 inversely. So I'll put T1 here is equal to this condition here, P2 relating directly to V2 and V2 relating directly to T2 when P or when pressure is constant. And that gives us the third row in or what we are calling the combined gas equation. The combined gas equation. So you'll find that the combined gas equation is one of the best in terms of illustrating. When we have the upper part, it gives us Boyle's law. When we look at this V1 T1, it gives us Charles' law. And so viewers, I would like us to move to example number 1. Example number 1. In example number 1, I'm going to give the illustrations, and then as we work through, I'll give you some questions which you'll try on your own, and then we shall be able to check on the expected answer. Let us write this together. We have a certain mass of a gas, example 1. We have a certain mass of a gas, occupies 150 centimeter cubed, occupies 150 centimeter cubed at 20 degrees centigrade, and at a pressure of 648 pascals. Now, the question is, calculate the volume of the gas, at 101 325 pascals. 325 pascals at 100 degrees centigrade. At 100 degrees centigrade temperature. I want to read that again to confirm. A certain mass of a gas occupies 150 centimeter cubed at 20 degrees centigrade and at a pressure of 98,648. This is 98,648 pascals. Calculate the volume of the gas at 101,325 pascals. So in this particular question, we should be able to identify these conditions: the volume at condition 1, the temperature at condition 1, and the pressure at condition 1. So we are saying V1 is equal to 150 centimeter cubed. We have T1, which is equal to 20. Viewers, at this point, we need to introduce a very important concept in terms of how we relate Charles' law, and I believe we shall come back here briefly, how we relate Charles' law to the condition called temperature. That the temperature is calculated or is measured at the absolute temperature scale, what is normally called the Kelvin scale. So to convert 20 degrees to Kelvin, we add 273, and that gives us 293 Kelvin. And the pressure 1 is equal to 98,648 pascals. In condition 2, when we change conditions, we shall have V2 being equal to, that is what is asked, T2 is equal to 100 added to 273, and that gives you 373 Kelvin. Then pressure 2 is equal to 101,325 pascals. In this case, we are going to obey, or we are going to use the combined gas equation. In the combined gas equation, we have the conditions of Boyle's and Charles' law being used. So the first thing, to earn marks, full marks in this question, we write the equation. P1 times V1 over T1 is equal to P2 V2 all over T2. And substituting, therefore, at this level, we are going to get the values as 150 times, that is P1, maybe we start with P1 at 96,648 times V1, 150, all over the temperature 1, 293, which is equal to, we look at P2, that is 101,325 times V2, which we are looking for, all over 373. At this point, we make V2 the subject of our working, and we shall have 98,648 times 150, cross multiply with 373, we divide by the 293 and 101,325. 101,325. And V2, viewers, punch that on the calculator, and let us see what we should be able to get. Approximately, we are getting 181.14. 181.14. That is 181.14 centimeter cubed. 181.14 14 centimeter cube. Straight away, let us look at question 2 in the next working. However, before we move to the next working, I would like us to put a condition here about temperature. That when we are on Charles' law, this is something that we can add very well here. When we are on Charles' law, the temperature is measured using the absolute temperature scale. So we say that for a given fixed mass of a gas, the volume of the gas is directly proportional to the absolute. I'd like you to add the word absolute. The absolute temperature. This is temperature which is measured using the Kelvin scale, whereby the degrees, the temperature in degrees Celsius, we add 273 to give it the scale, Kelvin scale. So the word here, temperature in the absolute scale, is extremely important. With that, we go to question number 2. Example number 2. We have a fixed mass of oxygen has a volume of 100 centimeter cubed and 25 at 25 degrees Celsius. So we have the condition, first conditions, 100 centimeter cubed, and the temperature is 25 degrees Celsius. What will be its volume at 15 degrees Celsius if pressure remains constant? So, viewers, we can take this with the first, with the working of the first question, and in the solution we can put first the conditions. We have V1 being equal to 100 centimeter cubed. Then we have T1 being equal to 25 plus 273. So viewers, on our calculator, let us punch in that. We have 25 plus 273. That gives us 8, 5, this is 9, and 298 Kelvin. The P1 is a constant. This is constant, it's not changing, so we need not factor it here. We look at V2 is what we are calculating, and then T2 we're given at 15 plus 273, and that gives us 288 Kelvin. In summary, if we use the combined gas equation, using the combined gas equation, we have P1 V1 over T1 is equal to P2 V2 over T2, where P1 is equal to P2 leads us to make the conclusion V1 over T1 is equal to V2 over T2, and basically that is Charles' law. Viewers, I'd like us to make a remark drawn from what we had done in question number 1, that when we are dealing with the temperature falls under Charles' law. We have to use the absolute temperature scale, the Kelvin scale, and that we change the degrees Celsius to Kelvin, and that is extremely important. Substituting, therefore, the values, we get that V1 is 100 all over T1, which at this point is 298, which gives us V2 all over 288. So it's upon us to make V2 the subject of the formula. That's 100 by 288 all over 298. And viewers, I would like you to punch that on your calculator and see that to one decimal place, we are able to get 103.5 centimeter cubed. And with that, we can move on to the fourth row. In our notes, it is item number 5, what we call Graham's law of diffusion. Graham's law of diffusion. Graham's law of diffusion, and that is an item which I would like us to discuss here. What is diffusion? Diffusion is the movement of particles from their region of high concentration to their region of low concentration. So this gentleman called Graham discovered that when gases diffuse, the rate of diffusion is inversely proportional to the square root of their density at constant temperature and pressure, keeping those two conditions constant. We put it down and say that the rate of diffusion of a given gas is inversely proportional to the square root of its density, at constant temperature and pressure. So that is very important that we note the key items here. The key items being the inverse proportion of the rate of diffusion being inversely proportional to the square root of its density. And of course, keeping the temperature and the pressure constant. So the most important item for us to be able to remember is the way we rate. Let us make R the symbol for rate. You find that it is inversely proportional to the square root of its density, the density of the gas. What does that mean? If we remove the proportionality sign, we shall have the rate of diffusion is equal to given constant divided by the square root of the density of that gas. And what does that create? That creates that if the gas was A, we can use density A like that. That enables us to have a relationship between the rate and the density. We make K the subject of the formula by multiplying by the square root of the density A on both sides, and that will lead us to the rate of a gas A multiplied by the density of gas A is equal to a given constant. And that leads us to a situation whereby now we can compare two gases. We can compare a gas called A and another gas called B. How is the relationship? We can relate this one as the rate of gas A multiplied by the density of A is equal to the rate of gas B multiplied by the density of that gas B. And that will give us a constant. Now at this point, if we divide out by the square root of the density of B on both sides, maybe since I want the rate to be the one dividing out, so let us divide by the rate of B on both sides. We divide by the rate of B. What do we get? That this cancels out and we arrive at rate of A all over the rate of B is equal to, that multiplied by this one, the density of A will be equal to the density of B. At this point, we divide by the square root density of A, we divide by the square root density of A. This cancels out And at this point, therefore, we make a very good conclusion that, therefore, we can have that conclusion, rate of gas A all over the rate of gas B is equal to the density of gas B all over the square root density of gas A. And that marks our first equation in terms of relating or comparing two gases. Continuing with this relationship, we get that since density is proportional to molecular mass, since density is proportional, to molecular mass, that is a very, very important concept. Density is proportional to molecular mass. What do we get? We get that we can relate rate and density directly. That is, where we have rate of A to the rate of B, we have a direct relationship with molecular mass, whereby density of B over the density of A. Now, this gives us molecular mass of B all over molecular mass of A. This is the meaning of what we have written, that density is directly proportional to molecular mass. However, we are seeing, just like density, rate is inversely proportional to molecular mass. Rate is inversely proportional to density. So that relationship, we are able to get a second relation, which we are going to say the square root of density of B all over the square root density of A is equal to molecular mass of B all over the molecular mass of A, which is equal to, now we pick on this one, rate of A all over rate of B. Viewers, I would like us to specifically highlight this portion here. We highlight that portion and we call it equation 2, which relates molecular mass and rate, the square root of molecular mass of B and rate of A, square root of molecular mass of A and rate of B. Now, we move on to a third portion, a third very, very important area on how we relate to time. You find that time is inversely proportional to the rate. Note, we have an NB, time is inversely proportional to rate. Time is inversely proportional to the rate. And what does that mean? What is the meaning of that? It means that when you have the rate of A to the rate of B, it is equal to the time of B all over the time of A. The rate of a gas A is inversely proportional to its time. Practically, it means when a gas has a very high rate of diffusion, it takes a very short time. And the reverse of that, when a gas has a very slow or a very long, a slow rate of diffusion, it takes a very long time to diffuse. In summary, if we can put all three rows together. Let us do a summary here. We have a summary. How do the three rows relate? In number one, we saw rate of A over the rate of B is equal to the density of B over the density of A. This is number one here. In number two, we did see rate of a gas A being compared to the molecular mass, and that one is equal to molecular mass of B all over the molecular mass of A. And in number three, we have seen how rate compares with time. It compares with the time, and that is a very, very good summary. However, an item that we need to talk about here is that during all these issues of comparison, we need to compare equal volumes. So that is a very important item as a note, that we can only, in our calculations, we can only compare the rates of diffusion. We can only compare the rates of diffusion of two gases if their volumes are equal. If their volumes are equal. Extremely important. And that means that in the calculations that we shall meet, we shall need to have the volumes equated, and then we check on their rate of diffusion. So viewers, what is next? We are going to look at about 3 questions involving Graham's law of diffusion. In some of the examples that we shall have, either example 1 or 2, we shall ensure that we are comparing equal volumes, and then in the other one, we shall change and try to have the question having different volumes, such that we shall have, first of all, to equate the 2 volumes. So let's move on to example number 3. In question number 3, we have 60 centimeter cubed of ozone gas diffuses through a semi-permeable membrane in 80 seconds. So we have 60 centimeter cubed is our volume for the ozone gas, and it is diffusing in 80 seconds. The question is, calculate the time taken for 90 centimeter cube of nitrogen 4 oxide gas to diffuse under the same conditions. Now, viewers, in this question, we are required to find the time. One thing we need to recall the formula for time. We shall have the molecular mass of B all over the molecular mass of A is equal to the time for gas B all over the time for gas A. Time for gas B, since we had said if we put rate here, we'd have rate of A being inverse to time A. We'd have rate of B inverse to that. However, the rate and molecular mass are going to have some inverse variation also at that point. So since these are the 2 conditions necessary, we can look at them. The other item that we need to seriously look at is the issue of different volumes. We are having a situation whereby 60 centimeter cubed of the ozone gas, O3, diffuses in 80 seconds. 80 seconds. Now, since the nitrogen 4 oxide is not 60 centimeter cubed, what we do is we try to see if this ozone gas were 90 centimeter cubed, what time will the ozone take? So we check at this point. Supposing 90 centimeter cubed of the ozone gas were available, it would diffuse in how many seconds? So we cross multiply, and that comes to be 80 times 90 divided by 60. 80 times 90 divided by 60. And that comes to be maybe we can do the division by 10 by 10. By 2, we get a 3. By 2, we get 40. By 3, 1. By 3, we get a 3. 40 times 3 is 120 seconds. At that point, viewers, we shall be able to comfortably compare equal volumes. How? If I may write at this point, the second star, we are going to say 90 centimeter cubed of nitrogen 4 oxide diffuses in what time? We are told calculate the time taken for that. So we shall be having that as our question mark. That way, we shall be comparing equal volumes, 90 of the ozone and 90 of the nitrogen 2 oxide. With this one, we have some items that we know. We know their molecular masses. We can calculate that one also. Therefore, the molecular mass of the ozone gas is 3 times 16, and that comes to be 48. Once more, we look at the molecular mass of nitrogen 4 oxide, NO2. That comes to be 14 plus twice the oxygen, that is each is 16, so that is 14 plus 32. We have 14 added to 32, and that gives you 4 added to 2 is a 6, and 1 plus 3, that gives you 46. Now, what does that mean if we, for instance, take this to be our gas A and this one to be our gas B? What does that give us in the formula? It means that we shall have the square root molecular mass of gas B, which is our nitrogen 4 oxide, 46, all over molecular mass of gas A, which is our ozone, that is 48, square root of that, and that is going to be equal to time B. Time B, our gas B is nitrogen 4 oxide, whose time we don't know. We are looking for it. Time A is the time for the ozone, and we are saying equal volumes, so we use 120 and not 80 because we need to compare equal volumes. This is a point we had said earlier on. So here we shall talk about 120 seconds. At this point, the task that we have here is to make time be the subject of the formula, and that means time of gas B, our gas B now changes to be the NO2. So we can change on that and say the time for NO2 will be equal to square root of 46 times 120 divided by square root of 48. Viewers, punch in that on your calculators and let's confirm if we get 117.468 seconds. 117.468, and that can be rounded off to 2 decimal places, 117.47 seconds or thereabout. So if you look at this kind of a working, you find that getting the formula correct, writing the correct formula there earns you a mark. This gives you a mark, 1 mark. Maybe I can put that one in a different color, and then we get it clearly, such that we have 1 mark at this level. Substituting in the formula correctly, all these values, we get the second mark, and then the correct mark for the answer, and that gives us 3 marks in such kind of a question. So it is important that where I have shown emphasis on converting one volume to be equatable to the other, this is a very important area. The same gas will diffuse in the same rate, so the volume here can allow us cross multiplication. But when the gases are different, then we do not do the cross multiplication. We have to follow the formula approach. Let's look at example number 4. Example number 4. In our example number 4, we have 140 centimeter cube of nitrogen gas, which is diffusing through a membrane in 70 seconds. So here we have 140 of nitrogen gas diffusing in 70 seconds. How long will it take 200 of carbon dioxide to diffuse through the same rate? In this case, we can now move a little bit faster since we know what we are supposed to do. We are going to say that 140 centimeter cubed N2 diffuses in 70 seconds. What about the unknown? If this nitrogen were 200 centimeters, how long will it take? It will take 70 times 200 all over 140. And that comes to be by 71 by 72 by 21 by 100. It will take 100 seconds. So viewers, you can now see how simple it is. We will be able now to compare equal volumes of different gases. We are going to put and say, what about 200 centimeter cube of CO2 gas diffuses in what time? So at this point, we are comparing equal volumes. The time of diffusion here and the time of diffusion at this point. So that is extremely important. What if the gases had equal volumes? We would not need to have this portion of the earlier working, of this working. So straight away, let's go to the formulas. The formula requires that the square root of the molecular mass of B all over the molecular mass of A in terms of time will be square root, or we shall be comparing to time of B over the time of A. That means alongside here, another item we need is molecular mass of nitrogen. The molecular mass of nitrogen is 2 times 14, and that gives us 28, since nitrogen equals 14. Those RAMs will always be provided at the end of the question. What about the molecular mass of CO2? It is 12 for carbon and twice 16 for the 2 oxygens, and that comes to be 12 plus 32, that gives you 44. So we have the 2 molecular masses. At this point, we can give who is who. Which gas takes B, which gas takes A. For instance, if we say that nitrogen becomes our gas A and CO2 becomes our gas B, then we follow and substitute equally to this formula and say, therefore that the square root, the molecular mass of gas B, that is CO2, is 44, all over the molecular mass of gas A, that's nitrogen, 28. That is equal to time for gas B, which is the time for CO2, we don't know, all over the time for oxygen to diffuse, that is nitrogen, to diffuse through is 100. At this point, we're going to make the time for CO2 the subject of the formula. And finally, we can say the time for CO2 will be computed by 100, which is cross multiplied here, times square root of 44 all over square root of 28. Viewers, punch that on your calculator and let us see what that gives us. I believe you've managed that, and it comes to be 125.35 seconds. 125.35 seconds. In our last question, we are going to compare equal volumes. That means we have two different gases, but their volumes are equal. And that takes us to example number 5. In example 5, we have 60 centimeter cubed of oxygen, 60 centimeter cubed of oxygen diffuses through a porous partition in 50 seconds. How long would it take 60 centimeter cubed of sulfur oxide gas to diffuse through the same quotations? Viewers, you realize that the volumes are equal. That is 60 of oxygen and 60 of SO2, that is sulfur oxide. However, the time for diffusion for oxygen is given as 50 seconds. So what we are missing, or what we are required to calculate, is the time taken by the SO2. So here, the question has given us a level ground. The volumes of the two different gases are the same. The volumes are equal. We compare equal volumes. So straight away, let us move on. We are going to, in our solution, we can say that the square root of the molecular mass of oxygen, the first gas, all over the square root molecular mass of SO2 is equal to the time taken by oxygen to diffuse over the time taken by SO2. In this case, the time for the oxygen is given. We shall look for this one. We need to identify and calculate out the molecular masses. So before we substitute, let's get the values. Molecular mass of oxygen is equal to 2 times 16, and that is 32. Molecular mass of SO2 is equal to 32 for sulfur plus twice the oxygens, that is 32 plus 32, giving you 64. So now we have all the items that we need. We can do the substitution. Molecular mass of oxygen is 32, so square root of 32, all over square root of molecular mass of SO2 is 64, and that gives us the time for oxygen. We have been given the time for oxygen as 50 seconds, all over the time for SO2. So our task here is to make the time for SO2 the subject of the formula. And how do we go about it? We can multiply both sides by time for SO2, multiply by the time for SO2, and that this will go, so that we shall have time for SO2 multiplied by 32, root of 32, root of 64 is equal to 50. Now, mathematically, we say multiply by the reciprocal. So on each side, we multiply by the reciprocal to this and the reciprocal to that. So this goes, and we are able to have time of SO2 being equal to 50. So here we had multiplied by root of 64 over root of 32, and so we get root of 64 all over root of 32. And I would like you to punch that on your calculator And let us check on what we have. This can be equated as 50 times root 2 because the square root can be distributed across the division. And that gives us approximately 70.71 seconds. So in this kind of a calculation, we can see the working is slightly lesser because the volumes are the same. So we only need now to incorporate the formula and we are able to get that. So the formula is very critical, M1. The substitution into the formula at this level is very important, and then the answer is very important. And the 3 marks are so scored. Viewers, we have had a very good interaction in terms of how well we do the calculations in Graham's law when the volumes are the same and when they are different. So, like in this case, the volumes are the same for the 2 different gases whose rates we are comparing. Here, I have an assignment for you. I would like you to work out this question, which says that 100 centimeter cubed of ethane gas, 100 centimeter cubed of ethane gas. Ethane gas goes by the formula carbon, hydrogens 3, another carbon, 3 hydrogens. That is the formula for ethene. Let me get that properly. The formula for ethane. So it diffuses through a polar spot in 100 seconds. Then we have another gas called Q. We are required to calculate its molecular mass if 100 of it. So you can see the volumes are the same volumes, but gas Q diffuses in 121 seconds. And we are saying that this diffusion will occur at the same conditions of temperature and pressure. So all what we have changed is the nature of the gas. The expected answer is 43.923. With this, viewers, I would like us to end our lesson there. I would like to thank you for having joined me in this long topic, which is a topic in Form 3 chemistry. I would like you to share this video, subscribe on it, and make your comments. Any question, you can post it on the comment section. We are moving on with the series of lessons which touch on some of the challenging topics across various classes from Form 1 to Form 4 in mathematics and chemistry. Coming up next, we shall be looking at the mole. Calculations in the mole and how you go about it to do the items you are required to have in the mole concept. I would like to thank you for the continuous subscription and let the channel grow. I've been your teacher, Mr. Steve Getao. See you next time.